This video deals with double sideband suppressed carrier, that is DSBSC. So we would be looking into this modem, that is the modulator on the transmit side and demodulator on the receiver side. So this is the Simulink block for double sideband suppressed carrier DSBSC, where over here we have the modulator, and over here we have the demodulator. So the detailing of it would be done at the end of this video. So let us first focus on the modulator aspect. So in the modulator, we have a message signal M of t, and this is a low frequency signal that we need to modulate. So this signal can be a simple sinusoid or a human voice which is having a low frequency. So over here, M of t is representing a signal in time domain which is operating at low frequency. So you can observe that if this is our M of t, and if we take the Fourier transform of this signal, so we would have M of f, and the bandwidth is b hertz. So in short, this is our modulating signal which is in the baseband frequency. So this modulator is nothing but a multiplier. So we have this multiplier block whereby we multiply a simple sinusoid, that is cos 2 pi fc, having an amplitude of AC, right? And fc is our carrier frequency. So this whole function we can call it as c of t, which is plotted over here. And the c of t is a high frequency signal which is simple sinusoid. Over here we simply have a cos function. So this is having an amplitude of AC, so it is oscillating between plus AC and minus AC, and the time period is simply this until here. So this is our T naught, which is equal to 1 over FC. Now again, in terms of the frequency domain, so we have C of F. So we have two delta function, because this cos function we can break it down into 1 by 2 e to the power plus j theta plus 1 by 2 e to the power minus j theta. And then if we take the Fourier transform, so for an exponential function we have a delta function. So this is why we have a delta function, delta of f minus fc coming from here, and then delta of f plus fc. So two delta functions stationed at plus fc and minus fc. So this is our carrier. So the message signal, local oscillator, which multiplies a simple sinusoid, that is AC cos 2 pi fct with the message signal. So at the output of this oscillator over here, that we have represented by phi of t, so this is basically our DSBSC signal, that is double sideband suppressed carrier signal in time domain. Now if we multiply these two signals together, this is slowly varying in time, and this is having a high frequency, that is it is varying quite quickly with respect to time. So if we multiply these two, so we would eventually get this signal, whereby we would have an envelope based on the low frequency signal, and within that envelope we would have a high frequency that is coming from the oscillator. So at these phase shift points, at these points, because we are moving from plus AC to minus AC, so when this changes from positive to negative, we would have a phase shift. So whenever we would have a zero crossing, we would have a phase shift. So this plot is just a multiplication of the initial two plots. How can we determine its Fourier transform or its spectrum? That is phi DSB SCF. So using a simple property that if we are multiplying in time domain, so in the frequency domain we are convolving, right? So this means that this signal is going to convolve with this signal, right? And from the property of a delta function, so if any signal convolves with a delta function, then that signal would shift to that delta function. That is why this plot is now shifted to plus fc and minus fc as is. So now we have the time domain plot of double sideband express carrier as well as its spectrum. So note that this is the signal that we're going to transmit over the air, right? This is the signal which is an AM type, that is double sideband suppressed carrier. So why do we call it as a suppressed carrier? This delta function is the carrier. In the transmitted wave, we do not have a carrier, right? So this carrier is not there. So since we are suppressing this, so that's why we have the terminology that is suppressed carrier. Now observe that in the original message signal, the bandwidth was B hertz, and the bandwidth of carrier signal is simply zero because this is narrow band. Delta function does not have any weight. The bandwidth of carrier is simply zero, whereas the bandwidth of modulated signal is from this point until this point, that is 2b. So this is our carrier frequency fc, fc plus b and fc minus b. By transmission we have increased the bandwidth of pass band. So this is our pass band frequency, and for that the bandwidth is now 2b. Now again let us replot the baseband and the pass band. So over here this is our upper sideband, which is also over here and over here. So these are our upper sideband, whereas this is our lower sideband, and this is represented over here. Also note that for m of t, if this signal belongs to real number, then the spectrum is even function. That is, whatever is over here, it is also replicated over here. This is easily observed in this signal. This means that this information is reappearing over here in the negative frequencies, but since the bandwidth was from 0 to positive frequency, so it was not having an effect in terms of bandwidth. But after modulation, now the bandwidth has increased to 2b, and within that we have redundant information. That is, whatever is over here, it is being repeated over here. So we are wasting some bandwidth, and hence is not very efficient, but it is a very simple technique nevertheless. Now mathematically speaking, phi of t is simply this message signal m of t times this signal, that is AC cos 2 pi fct. So this is the signal that we are transmitting. So assuming that the channel does not affect the transmitted signal, and next in the demodulator aspect, we want to recover the original message signal, that is a low frequency signal, right? So what we do is this signal, which was DSBSC signal, this signal, we multiply it again with the local oscillator, which is having exactly the same frequency as the one used in the transmitter side. So at this point, let us call this point as W of t. So W of t would simply be the phi DSB SC of t this signal multiplied by the local oscillator, which is cos 2 pi fct. So note that this signal is simply AC m of t cos 2 pi fct, and from here again we have cos 2 pi fct. So we would have an AC m of t cos square 2 pi fct. Let us visualize this signal in time domain. So if we have this function as a cos function and we take square of it, so the negative lobes would be rectified up. So if we multiply this with the message signal represented over here, so eventually we would have a signal which is again having this shape, but now we have which is w of t. Cos square of theta is equal to 1 by 2 plus 1 by 2 cos 2 theta. So from this trigonometric property we can simplify the third equality over here. So we can have AC by 2 m of t plus AC by 2 m of t cos 4 pi fct. So from this expression we have covered the w of t, but since we are interested in the low frequencies in demodulation, hence herein we will apply a low pass filter to reject this part. So we would be left with AC by 2 m of t, and this is our low pass filter, and this is k dash m of t, right? So where k dash in our case is simply AC by 2. So this was an end-to-end modulation and demodulation of double sideband suppressed carrier. So before moving to the simulation, let us again look into the frequency domain. So low frequency uh, narrow band from the carrier. So if we convolve this with this, so this would be appearing twice at each end, and this is drawn over here, and then we again have this carrier represented over here. So over here the spectrum would be 0 2fc minus 2fc. So this function now would go to 2fc and 0. Similarly, this function would now go to minus 2fc and 0. But we are interested in low frequency, so we'll pass it through a low pass filter, and eventually we would have some factor k dash m of f. So this is our demodulated signal. Now let us visualize all of this process in Simulink. So this is the double sideband suppressed carrier that I have discussed. Over here we have the modulator on the left side and the demodulator of double sideband suppressed carrier on the right side. So all of these blocks are available in the library browser given over here, right? So initially I use a message signal, and this is simple signal generator function that we can find from the library browser. I have selected sine wave, so there are multiple options: square, sawtooth, and random. Note that the design parameter for all four of them would change. So let us consider the single tone for the time being, that is the sine wave. It has a frequency of 100 Hertz. Then again I use the same block, that is a signal generator, but now I use it as a carrier frequency, that is C of t. Again a sine wave operating at 2000 Hertz. So this was at 100 Hertz. The carrier signal is operating at 2000 Hertz, that is 2 kilohertz. Next I have a modulator. So in the modulator, I have fed the message signal and the carrier, and then the output of this modulator is basically a double sideband suppressed carrier signal, right? So all of these blocks are for visualization. So this is a simple scope, and these three are for spectral analysis. So on the receiver side, we again have the same carrier as in the transmitter side, and now we use a demodulator block, and after that low pass filter as in our earlier discussion, again a scope, and then some spectral analysis of the output. So let us run this simulation. So in this scope, the first feed is of the message signal, the second feed is of the carrier signal, and the third feed is the modulated signal. So let us visualize the time domain plots. So this is our message signal, this is our carrier signal, and on the lower side we have the double sideband suppressed carrier modulated signal, or in other words, modulating signal, carrier signal, and modulated signal. So in terms of spectrum, note that we have used a zero order hold with this sample time throughout. This is our spectrum of the message signal, which is roughly at plus minus 100 Hertz as defined earlier. This is the carrier. So again, the carrier is across 2 kilohertz. So we have roughly 2 kilohertz plus and minus over here. And then this is the double sideband spectrum, that is the spectrum of the transmitted wave. And herein you can observe that the spectrum showing at 1.9 kilohertz and 2.1 kilohertz, and at 2 we do not have anything, that is the carrier is suppressed itself. The carrier was at 2, but it moved the original frequencies of 100 hertz to 2.1 kilohertz and 1.9 kilohertz. So this is the spectrum of transmitted signal. Now on the receiver side, in the demodulator, again we multiply with the carrier signal and we set the carrier signal exactly in sync with the transmitted carrier, the local oscillator at the transmit side. After that, we pass it through a low pass filter, and I have selected a basal low pass filter. This is under analog filter design. The order is 8, and I have set the cutoff frequency to 500 Hertz. Then we have some spectral analysis of the received signal and the scope of input signal coming from here. The second feed is output of the demodulator, and the third feed is output of the low pass filter. So let us visualize this plot. So over here again, this was our message signal. This is the plot of the output of double sideband suppressed carrier demodulator, that is over here. So whatever was the input, we multiply with the cos function. So this cos multiplied with the original cos, so we have a cos square. So this is why we have this plot. We have already discussed this in the discussion session earlier as well. And you can observe that there is a low frequency content and there are higher frequency contents within this. So if we use low pass filter, so we can reject the high frequency contents and we can recover the low frequency signal, and this is something that we have done over here. So you would observe that the shape is exactly similar, that is, this was the message signal which we modulated, and this is the received signal that we eventually got, right? But you would observe there is some phase shift. So we have a phase shift roughly this edge is moving towards right, so this is the phase shift. Note that this phase shift is originating from this filter. So this is an inherent property of filter, that it introduces delay. But if this phase delay is linear, it would come under the distortionless system and it would not affect us. But if it is non-linear with frequency, that is, it is different at different frequencies, then we would be having some problems.